All right, what we're going to talk about here next is, let's try to figure out, we've got this plane and then we've got another plane angled in on that. We want to know, okay, so what about that angle theta between those planes? Can we figure out what that angle is? Using a little mathematics here. Well, maybe hard to see some of these things on it. Let's just look at the cross sections. So we got a cross section. It's just two lines, and the angle we're talking about here is theta. So we got this plane looking at the side view there, if you will. We're just looking for that angle theta. Well, turns out, that's maybe a little complicated, but if you look at this, if you look at the normal vector to this, to the one here that going across ways like that, the normal vector would be like that. And then the normal vector to this angled plane, if you will, would be coming in like that. And the good news is, think about it a little bit, the angle between those two normal vectors, it's going to have to be the same angle because they're perpendicular. I mean, we could go through geometry stuff there, but I don't think it's too big of a stretch to figure out that those two things, those two angles are going to be the same. The angle is the same between the planes as it is, or between the normal vectors as it is between the planes. So we're going to play off of that because we know how to calculate an angle between vectors. We actually just talked about that in a previous example, I think, or a couple examples ago. So the angle between the vectors is the same. So yeah, it turns out if you do the dot product of two vectors, that equals the magnitude of n1 times magnitude of n2 times the cosine of the angle between them. It's the dot product. And so there, if we solve for cosine theta is the dot product, n1, n2, divided by the magnitude of n1 times magnitude of n2. And then do your arc cosine. Yeah. So, the angle between planes, we're just going to use our little trick there for the angle between vectors. Because if you've got a plane, you got to know its normal vector. So you know its normal vector. Pretty much straightforward from that. Now, this is, of course, if we've got an angle between the planes. First thing you check when you have two planes is whether or not they're parallel. So look for that. So find the angle between planes if they aren't parallel. Right? That's kind of like parallel lines or lines. They can either be parallel or they can intersect. Same thing on the planes. Parallel or intersecting. Okay, so number one here, let's look at this one. So we've got 3x minus 12y plus 6z equals 1, and 2z equals 4y minus x. So in either case, if they're parallel or if we want their angle between them, we need their normal vectors. What's the normal vector here? Well, the normal vector here is 3, negative 12, 6. Now, sometimes they a little tricky about it. And they'll give us a plane in a little different format than we need. Yeah, to get the normal vector from this, we need all the terms on the same side, x, y, and z on the same side. So it doesn't matter. X minus 4y plus 2z equals 0. So we'll bring those over first. And so we've got the normal vector here, call it N2, is 1, negative 4, 2. And so that's where you want to check whether or not they're parallel, first of all. And again, remember, they're parallel if which I guess it's the other way around in this case, but easier to see, but well, I guess you can look at it either way. Yeah, so if one normal vector is a multiple of the other normal vector, you got parallel, which is what we've got here, isn't it? Yeah, we've got, I guess the easiest way to see it, you got, yeah, N1 is 3 times N2. Yeah, that's, isn't it? Yeah, perfect. Multiply by 3 on each one. So the normal vectors are parallel, which means also that's how you tell if the planes are parallel. So which means they don't have an angle between them. They never meet. All right. Let's try number 2 here because I don't think they are parallel. All right, so we got 6x minus 2y plus 3z equals 7, and the other one is 4x plus 5y minus 7z equals 11. Those are my 2 planes in this case. Okay, so yeah, that's N1 here is 6, negative 2, 3, that'd be the normal vector here. The normal vector here would be 4, 5, negative 7. And that is not multiple. Those aren't multiples of each other, right? Let's see. We have to multiply 4 by 3 halves. No, something, but yeah, they're definitely not multiples. All right, so to get the angle between them, we said then, so the cosine of theta is equal to the dot product divided by the magnitude, product of the magnitudes. So what does that give us? Dot product, well, you just multiply the components and add them together. So we got 24 plus negative 10 plus negative 21. Magnitude of N1, where you do your square root of your squares added together. So that'd be 36 plus 4 plus 9 times magnitude of N2, which would be the square root of 16 plus 25 plus 49. Was that negative 7 on top, and then the square root of 49 times the square root of 90? Did I do that right? 80. 90. 7 squared root of 9. So cosine of theta equals negative 7 over 7 squared root of 9. And we can simplify, but really what we're going to do there to get the angle, so then theta is the cosine inverse of negative, oh, that would cancel even. Just call it -1 over square root. And then we can simplify it more. However you put it in, should get it to us there. And it probably should be in radians, so keep that in mind. This gives me a 1.6764, blah, blah, blah. That's radians. So if I wanted the degrees, change the degree mode, but let's just multiply by 180 over pi, that'll give us degrees. That's what they want. I think that's probably what they want. 96.05 degrees. Two decimal places anyway. Is that okay? Is that what you got? I'll do that right? Rest your sorry. Okay. Well, let's try. Or look at this. The line of intersection between two planes. So we found the angle between two planes. What if we wanted to know where two planes intersected? So we've got this line here between the two. So kind of figure out that line. So I got this plane here, and then I got a plane coming in, angled on up there on it. Kind of figure out that line L. Well, what do we need for a line? Need two things, right? Need a point, and then you also need a vector for the direction, right? Yeah, so in 3 dimensions you need a point and, well, you know, in 2 dimensions you need a point and a direction. We could call it the slope, though. In 3 dimensions, the direction is called the vector. So anyway, so a line you need a point and a vector. All right. Well, I need a point on that line, so it could be any point whatsoever. So what's the specialness about that point? It's in both planes, right? So the point I need is just a point in both planes. One way to do it is you know, it can be any coordinates whatsoever. It just has to work in both planes. X0, Y0, Z0. We need that point there. So one thing is, let's just try X as 0. And then solve for the y and z that go with that info. So we'll try letting x equals 0 and then solve, because yeah, remember we're going to have think about this. 2 planes, probably, at least we can get it put it into that form. So we're going to have two equations basically like this. So what we're saying is let x be 0. And what that sets up is a nice little system, right? A YZ system. Worst comes to worst, if x is 0 doesn't work, try x is 1 and you can move that. That'll just be a number then, and you can move it over and you still have a system, okay? So it's basically you're just solving a system. Try letting x equal 0 and solve the system for y and z. And if y is 0 gives you, I mean x is 0 gives you an unsolvable system or something's screwy about the system, use another value for x, okay? So it's usually not too bad. All right, now for the vector, okay, so let's think about this. For vector v, I need vector v here for that line. How can I get that? Well, let's think about it. Vector v is in both planes as well. So here's what that means. I need, let's think about vectors and planes again. When I have this equation, I've got real handy, I've got the normal vector, right? So the normal vector for this plane, and then the normal vector for this plane, those are whatever angle, but think about this. V is in both planes. So if V is in this plane, isn't it perpendicular to that vector? And if V is in this plane, yeah, perpendicular to that. And if V is in this plane, is perpendicular to that vector, right? Because that's the normal vector for plane 2. So it's perpendicular, it's a vector that's perpendicular to the normal vectors. What does that make you think of? Cross product. So V, vector V of this line is the cross product of N1 and N2. Easy as that. So that's how you get, and then you put all that information into your line format. Let's try it. All right, so find the line of intersection for 3x minus 6y minus 2z equals 15, and 2x minus y minus 2z equals 5. All right, well, N1, let's call it here, is 3, negative 6, negative 2. And N2 is 2, negative 1, negative 2. Those are just the normal vectors. And so vector V of our line, the direction of our line, is just the cross product. And however you want to get that, but line them up with IJK like this, then do your determinant, that'll give you your cross product. So here the cross product is going to be the I component. So the I is going to be the determinant of negative 6, negative 2, negative 1, negative 2, minus then the J component. So the cross product of 3, negative 2, negative 2, negative 2. And then the k component is the cross product, cover those two up. 3, negative 6, negative 2, negative 1. So vector v is, what is that, 12 minus 2. The j would be minus negative 6 minus 4. And then k is negative 3 plus, make some formats here, I guess. Just the way it worked. All right, negative 3 minus 12. Get that right? 10, and then 10. No, what did I do wrong? That's maybe something by 4, for sure. Write something down. I got a different answer on my paper, so that's what's throwing me off. Oh, I've got 2. Ah, that's what it was. This is positive 2, sorry. Positive 2. That does change. So yeah, that is plus 4. That is negative 3 plus 12. Yeah. So vector v is 10, positive 2, positive 9. That's what I got before, so if anybody checks me wrong on that, just let me know. I did have that. I had that wrong. Copied that down wrong. That'll always mess you up. Okay, so that's our direction of our line. What else do we need? We need a point on the line. So we're going to let x equal 0 for each one of these. So that'll be 0 minus 6y minus 2z equals 15. That'll be 0 minus y minus 2z equals 5. So just have a little system there to solve. Multiply, made this one real easy. Multiply by negative 1 on the bottom. Then you got minus 5y equals 10. So it looks like y then would be, in that case, negative 2, which would make z, plug that in for my y. So that would be 12 minus 2z equals 15. So that would be negative 2z equals 3. This equals negative 3 halves. And so our point on the line would be 0, negative 2, negative 3 halves. So we take that point, this vector, and let's just use parametric form. So x equals, it'd be 0 plus 10t. Set it up in the parametric form. The y would be negative 2, the point, the y component of the point, plus 2t. And then z would be negative 3 halves, negative 1 1/2, plus z component over there, 19. It's a line of intersection.